Okay, I can start.
Right, so good afternoon everyone. Welcome to the session on flat holography and the final day. Over to you, Raffaele.
Okay, thank you very much. First of all, I would like to thank the organizers for this opportunity to speak in this very, very interesting workshop, intensive and interesting workshop. And I will speak about spinning the flat limit of CFT correlator of spinning massive amplitude. This talk is based on these two papers, done in collaboration with Costas and Multanjay Verma. So, this is the plan of the talk. In the first part, I'll try to convince you why it's interesting to study the flat limit of massive fields, spinning fields. In the second part of the talk, I introduce the main ingredients of the talk. In other words, I'll describe the CFT correlators of spinning operators in momentum space, and the dual theory, which is essentially a complex Proca theory. And for this twin ingredient, I will study the flat limit of the 3 points, and then arrive to the conclusions. So, I want to start from the holographic principle, this nice idea formulated by Toft and Susskind, essentially because it was inspired by the fact that, as you know, the entropy scale as the area of the horizon instead of the volume. And the holographic principle, as you know, say that in quantum gravity, the physics in the interior of a region can be completely fixed by the degree of freedom on the boundary of this surface. And the most concrete realization of this principle is the ADS-CFT duality, which in its most general formulation is an equivalence between a d+1 dimensional gravitational theory on an asymptotically flat DS background and a conformal field theory which lives on the boundary. The most studied case is the duality, the equivalence between string theory on a DS5 cross S5 and n equal 4, d equal 4 super Young and Mill, and there is also a precise connection between the parameter of the string theory, the coupling constant, and the DS radius, with the coupling constant or the Toft coupling in the gauge theory. You can see that the G Young Mill is related to G string by this relation, and there is also a relation between the ADS radius and the Toft coupling. Due to this relation, just few years after the formulation of ADS-CFT, Polchinski and Susskind observed that if you take the limit that n goes to infinity, this corresponds to a geometry where the dual geometry becomes flat, and therefore you should recover string theory in flat space. Of course, this is also true in the most general formulation of the CFT. You expect that when the ADS radius goes to infinity, you should recover quantum gravity in flat space, and therefore you could have insight of quantum gravity in flat space by studying the flat limit of ADS-CFT corresponding. Furthermore, the flat limit creates a link between the theory on ADS and the theory in flat space. And due to this link, for example, you could also fix the electromagnetic form factor in ADS from their values in flat space. In fact, as we will see in the model that I'll discuss in this talk, we will see that the geomagnetic factor of the Proca field on ADS are exactly connected with the geomagnetic factor in flat space. But there is also another reason to study the flat limit of a massive particle. And this is related to the fact that now the people is trying to understand how much general is the holographic principle. And there is this formulation that, which is the flat holography, that says that maybe this duality, instead to work on a DS background, could be also works on a d+1 dimensional gravity in asymptotic flat space-time and a lower d or d-1 field theory located at infinity. And maybe this flat holography could follow from the flat limit of ADS-CFT Indeed, this is been shown in the case of a master's particle, as been shown in this paper, and we have also a very, very nice talk on this subject by Romain. But in the case, in this paper, you can see that effectively for massless particle, the fluctuography follows from the flat limit of a DSCFT. But for massive particle, the situation, in my opinion, is still a bit messy, because I have seen that there are papers where they propose that the dual theory lives on A plus A minus, there are papers where the dual theory lives on A0. So I think that the first step to understand the fluctuography in flat space is to study in a very precise way the flat limit in the case of massive particle. And this is the subject of this talk. In this setup, in this very physically interesting setup, we will study the flat limit. In particular, we will consider 3 points. Okay, I will work in momentum space and in a DS, in Euclidean a DS background. And in this, so in this setup for the dual theory, I'll consider 3 points conformal field theory correlators with a conserver current and 2 spin-1 operators. And on the other side, I consider a Proca theory on a DS background. And in this setup, I'll compute this, let me say this Witten diagram. I'll show you how to get the corresponding amplitude in flat space from this Witten diagram. But the first problem is that both sides of this equivalence are unknown in flat space. So first, we have to construct these 2 ingredients, and then we can compute the flat limit. So let's start from the conformal field theory side. So the 3-point correlator in momentum space between a conserver current and 2 generic non-conserver spin-1 field with arbitrary dimensional conformal delta is given by this expression. As usual, when one studies this conformal correlator, one separates the longitudinal part from the transverse part. In this talk, I'll just discuss about the transverse part, because we want to connect this correlator to on-shell flat amplitude. But in the paper, it's also discussed the longitudinal part, it's also discussed the spin-2 case. So, and this correlator is fully determined by computing the conformal field theory word identity. In other words, you have to impose that the correlator is invariant under dilatation and special conformal transformation, and of course you have to perform an ansatz on this correlator. And this is the most general ansatz for the transverse part. There is also a longitudinal part for these correlators. As you can see, involve 9 form factors that are written down, but you impose the conformal word identity, the primary and secondary word identity, and you can fix everything. And this is the results. As you can see, this form factor depends on the modified Bessel function. There are a certain number of fixed constants that you can read, A1, A5, and so on. There is also this antisymmetry exchange μ1, P1, μ3, P3. But imposing the secondary word identity, you can see that not all these coefficients are independent, but just 3 coefficients are independent. And all the other coefficients can be expressed in terms of the independent one that we have chosen, A5, A4, B2, and so on. So this is one side of the duality. Now we have to move on the other side of the duality. In other words, what we have done, we have taken the most general Euclidean bulk action, linear in the gauge field, in interaction with the complex Proca field, in D plus 1 dimension, of course, up to 3 derivative terms. The most general bulk action that you can write contains many, many terms, but by integrating by part and performing field definition, you can just write the most general action in terms of these 3 coefficients, up to 3 derivative terms, where you can see there is the gyromagnetic term and the quadrupole momenta. okay, all the quantity are defined on the slide. Now, what do we have to do? We want to compute from the bulk side the same correlator because we want to connect the bulk with the boundary. So what do we have to do? First, we have considered a Fourier transform along the boundary coordinates. And then we have chosen the axial gauge. So in this setup, we have solved the equation of motion. We have solved the equation of motion at first order decoupling constant. Why at the first order decoupling constant? Because we are just interested in the 3-point function, 3-point correlator. And the 3-point correlator is a linear in G. So this current is truncated at the first order G. There is also a term G squared that we neglect. Okay? And as you can see, the classical solution depends on the bulk-to-boundary propagator of the gauge field and the bulk-to-bulk propagator of the gauge field. Okay, this is the most general action. Then we have done the same game for the Proca field, because we need also the classical solution for the Proca field. But in this case, we have just solved the Proca field at order G0. So at order G0. Now it seems mysterious why we solve just the Proca field at order G0, but this will become clear later, become clear just in 2 slides. And these are exactly the bulk-to-boundary propagator of the complex Proca fields. Okay, this is the value at the boundary of these fields. Okay, so furthermore, as a standard technique at the SCFT, we have also determined the relation between the mass of the Proca field and the conformal dimension of the dual operator. This relation is very, very important because remember that we want to discuss a flat limit keeping the mass finite. Therefore, we have to send L that goes to infinity, but also delta, the conformal dimension that goes to infinity, keeping m square fixed. So the flat limit that we are considering is a double limit, not a single limit. And this is an important point. So, of course, now we have the bulk theory, and therefore you have to compute the 3-point correlator from the bulk side. We know that the prescription is to compute the classical action on a shell because this is the generator of the QFT correlators. But the problem is that if you compute the classic action, this is divergent. Okay.
If you're setting delta to infinity, can you ensure that you're not getting a black hole in the bulk? Is delta much smaller than C?
No, because the mass is fixed. So the mass doesn't go to infinity. The mass is fixed. If the mass goes to infinity, I think you can get a black hole. But if the mass is fixed, so could be not a black hole. Okay, then you have to regularize, the action is divergent, you have to regularize when you are closer to the boundary, then you have to regularize the action, and you put the cutoff, and then you have to subtract, I am just saying in few words, the holographic normalization, but you can imagine that behind this word there are many calculations, in detail are in the paper, many technical details. And then I am adding the counter term that subtracts this divergence. Now, from this renormalized action, I can compute the exact renormalized 1-point function, is this one, corresponding to the emission of a conserved current. And this is the expression that we get. As you can see, it depends on the bulk-to-boundary propagator of the gauge field and from the current, which the current is a linear in G. The current is linear in G. Now, in order to get the full tricorrelator from the bulk side, we have to perform the 2 hexa derivative with respect to the Proca sources. Now you understand why I have truncated, I have just taken the solution for the Proca field to the order 0 decoupling constant, because the current is already to order G. G is the coupling constant, and therefore I need just to evaluate this current to order G0, because otherwise I get extra contribution that in the 3 points they don't give any contribution. So when you do this calculation, okay, you get a very, very messy expression. It's impossible to write on a slide, but a very, very messy expression. But the nice thing is that the bulk calculation and the boundary calculation are perfectly in agreement if you assume this relation between the coupling constant, the geomagnetic factor, quadrupole momento, with the boundary arbitrary coefficients. In other words, as you can see, okay, and there is also, this is important, the relation between the mass and the conformal dimension. That is also an important relation. So as you can see, the number of bulk parameters coincides with those of CFT parameter, and we span the full three-dimensional CFT space. Another thing that we have seen is that this matching is valid also for each term separately. In other words, if you just consider the geometric factor, this therefore turn off the beta, there is also correspondence with the corresponding CFT correlators. And this is because the bulk action remains invariant for any value of the coupling. This is also an interesting point. Okay, now we have constructed, yes?
You are assuming this equation?
No. We have the CFT calculation, which I wrote here, as you can see. This is the CFT calculation. Then we do the same calculation on bulk side. Of course, on the bulk side, the calculation do not depend on these arbitrary parameters, which are CFT data, but depend just on the bulk parameter, which are the coupling constant. And you have to compare the two expressions. As you can see, the comparison is not simple because the expression is very complicated, involves modified Bessel function. But when you compare the two expressions, you have matching if you assume this relation between bulk and boundary data. This is the way in which we have done this.
So you are assuming an agreement between the CFT calculation and the bulk.
We are not assuming, we see that there is agreement.
It's the same thing as the match with the conformal dimension. That's on the same foot.
You're adding this to the dictionary.
That's part of the
Yes,
dictionary.
Could I ask a question? Do none of these triple K integrals diverge?
They diverge singularly, but when you consider the full expression, divergence cancels. There is some term which is divergent, but when you consider the full expression, go in the region x that goes to 0, you can see that the divergence cancels.
The specific deltas that would be more divergences. This is the generic case.
Okay.
And even in the generic case, some of the triple case will have divergences, but the bulk of the expression is very small.
So can I ask also a question? So this delta scale we are taking to infinity in the end, right?
Yes.
So that means that you're considering not protected operators? Or?
What I'm considering is it's a generic. On conformal side, I'm just considering a spinning operator. So it's a generic operator.
It is, general. No.
But on the bulk side, I mean, you're using supergravity, right?
I use supergravity, Proca field. Yes, Proca field, which is this one.
But I mean, this will not be generically true, like I mean, for non-protected operators, right?
Yes, but I have for small coupling constant. I have just a 3 level on the bulk side, so I don't see the problem. I regulated the classical action, so I am really at 3 level on the bulk side. So now we have to consider the flat limit. We have considered the flat limit on the Poincare coordinates. This is the matrix, as you can see. And we have parameterized, in order to do the flat limit, we have chosen this parameterization. This parameterization was not exactly the same parameterization, but was also proposed in these papers. But for example, in this paper, they also study flat limit, but tau, as we will see in our case, is in Euclidean time, but they work in Lorentzian DS. In this case, it's not in Euclidean time, but is a spatial direction. So it's already proposed in this paper, but we use in a different way. And what do? We do the limit del that goes to infinity, z that goes to infinity, keeping tau fixed. Tau is the emerging direction in the flat limit, essentially. And in fact, you can see that if you plug in this position in the metric, you get this expression and you get immediately the flat metric, d+1 flat metric. And tau is an emerging direction. Now, I think I don't have time to see this. Here, I show how performing the non-Huygens contraction, I can obtain essentially the Poincaré group from the DS isometry, but I think there is no time to speak about this. Then let's now consider the flat limit of the bulk to boundary propagators. Let's start from the Proca boundary to bulk propagator. Remember that on the Proca field we have to do this double limit. Okay. Therefore, this flat limit of the bulk to boundary propagator is very important because, as we will see at the level of amplitude, this determines the external lag factor that we have to associate to the external states in Minkowski space. But this will be clear later. Now, this double limit, it's very, very tough double limit, but the main ingredient of this double limit is the uniform expansion of the Bessel function, which is written here. By using this ingredient and massaging the expression a little bit, this is not a simple task, we have got this asymptotic expression for the bulk to boundary propagator. Then the bulk to boundary propagator defines the Proca field, and when we plug in that expansion in the Proca field, we get this result. As you can see, we get this exponential factor with the factor k squared plus m squared. This is the energy. Therefore, this is the energy of the particle. Therefore, we can introduce a d+1 dimensional Euclidean momenta, so defined, in such a way this quantity becomes AQ0 times tau. Therefore, tau necessarily must be interpreted as a Euclidean type. So this is an emerging quantity in the flat limit. Furthermore, we have this structure for the polarization of the Proca field. And this is very important. You can check that this is transverse. This is very important because it will be used later in identifying the 3-point amplitudes. Okay, all the factors are defined here. You can do the same game for the gauge field in the flat limit, and you get this expression, and the same game, you do exactly the same game. As you can see, since the d+1 dimensional momenta is just identified, fixed by this condition, or the short condition, you see that there is an arbitrary sign, which should tell you if the particle is incoming or outcoming. Now, we have all the ingredients to study the flat limit of the 3-point correlators. But remember that the main ingredients of a 3-point correlator is the triple K integral. Therefore, we have to consider the flat limit of a triple K integral. And, but we have all the ingredients because the triple K integral depends on the Bessel function. We already performed the expansion of the Bessel function. Therefore, when you perform this flat limit of the triple K integral, you get this expression. As you can see, due to the fact that in the flat limit emerge an Euclidean time, you get the delta function over the energies here, in very, very natural way. This is the missing delta function that you have, that is necessary to have to interpret a d-dimensional correlator as a d+1 dimensional amplitude. But this is emerged very naturally in this flat limit. Okay. And indeed, if you send the limit L goes to infinity, the correlator takes this form. So as you can see, there are some factors overall which are related to the external legs, the bulk to boundary propagator essentially. The missing delta function, in the correlator there is also delta function of the momentum, I wrote it in the first slide. And this very messy expression, I can show you this expression. It's very messy expression, which seems really far from an amplitude. But we are here, we have not still used the external polarization that we identified in the flat limit of the bulk to boundary propagator, which are given here Now you have written the polarization now in Minkowski space. You perform the weak rotation. In fact, you can compare with the previous slide. You see that here miss an I. When you use this polarization, that messy expression becomes very, very simple. This is the results. And as you can see, this is exactly the 3-point amplitude that gives the interaction of a complex Proca field with an external gauge field. This is the relation. So this is a really, really nice result. There is another important point, yes, that the gyromagnetic factor here must be which is the gyromagnetic factor that we have introduced on the S background, must be identified with the gyromagnetic factor in flat space. So it seems that there is exactly this one-to-one correspondence. So finally, what we have seen, just a summary of the talk. We have solved, in the first part of the talk, we have solved the conformal word identity, defined the 3-point function, involving a conserved current and two non-conserved operator. Then we have computed the dual correlator, and we have found perfect matching. This is a new test of the SCFT correspondence. And the matching is valid for each bulk coupling separately. Then we have computed the flat limit of the correlator. And we have got exactly the on-shell amplitude of a complex Proca field in interaction with each field. Of course, when we did this matching is valid in the infrared for the conformal field theory, because we are also performing a limit where z goes to infinity. So on the conformal field theory, we are in the infrared. Okay, in the flat limit, we also, I just show you that we also recover the Poincare isometry from the DS isometry. But in the paper, you can also find the flat limit of the bulk-to-bulk propagator in the cell gauge, and you can see that this perfectly coincides with the Feynman propagator in the axial gauge, of course. Now, you expect that our analysis will extend also a dagger point function. Furthermore, this approach seems also promising to get interaction between higher spin particle in flat space, because you can understand that on a DS background you have more symmetries that fix the coupling, and maybe performing the flat limit, one can get some insight on the coupling in flat space. Of course, one very interesting argument is to gain insight in flat space holography. Of course, we have just done here half of the story, the limit L that goes to infinity. We should do also the other side of the story, the boundary side, to see which kind of gauge theory we get on the boundary. So, thank you.
So, can you get the flat space limit of the generating functional directly?
Generic function?
Yeah.
No. We have just considered the correlator, 3-point correlator.
So, but you are expecting that this,
should work, but I would like to say explicitly, because the thing seems that work, but here in this argument, the devil is in the detail, really in the detail. So I expect that work, but I want to see explicitly how it works, especially on the 4th point. Yeah. Because you exchange a diagram and.
For just massless particles, there's this pattern where you take the total energy, something like it goes to 0, and for massive you've shown us how. But is there, suppose you have both massless and massive, is there a way to take it?
This is a case of massless and massive, because we have a photon with interaction with the two Proca field. The gradient that we have obtained is not pole, but the delta function, the momentum. This is the things that we get. So we see that emerge delta function should emerge a delta function, because we interpret the correlator as an amplitude. In amplitude, we have a delta function, not a pole. You need.
You can just take the masses to 0. We just take the delta function.
But you still take delta to infinity.
No, in the Maxwell case, it's not necessary. In Maxwell's case, no, I can show you, because I have on the slide. Maybe I was too fast, but I can show you. I have written also. Okay, it's here. This is the Maxwell's case. As you can see, we get again the exponential. Again, we can introduce a complex momenta. Again, tau is emerging. And therefore, as you can see, we get the missing, let me say, wave function along the time, also for the massless case. And this is essentially due to this parametrization, essentially, which is a good parametrization of the factoring.
Other questions, comments? If not, let's thank Raffaele again.